every night we stare into the dark, expecting answers from something that has been ignoring our calls for billions of years. Space, for all its dazzling beauty, is maddeningly mysterious. It's like a cosmic magician who keeps pulling galaxies out of nowhere, but never reveals how the trick works. The question of where does space end isn't new. It's been haunting human curiosity since the first person looked up, squinted at the stars, and thought, okay, but what's past that? Here's the thing about space. It looks empty, but it's actually a busy neighborhood. Stars exploding, planets orbiting, galaxies colliding, and black holes swallowing everything like celestial vacuum cleaners. Yet, when you zoom out, all of that cosmic drama becomes just a speck floating in a vast ocean of darkness. And that ocean? It doesn't seem to have a shore to. Imagine walking in one direction forever and never finding the end. That's space. It's the universe's ultimate commitment to ambiguity. If the universe had a "you are here" sign, it would be completely useless. We're floating on a planet, orbiting a star inside a galaxy. That's part of a cluster, which sits in a supercluster, which is one of countless other clusters sprinkled through space like cosmic confetti. Every time scientists think they've mapped something big, the universe casually reveals something bigger, like it's playing a never-ending game of hide-and-seek, and it's definitely winning. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes, it's best enjoyed the way you'd enjoy a late-night conversation. Quietly, with a cup of tea, and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift toward sleep, consider subscribing. No pressure. Only if you enjoy these calm journeys through the universe. Now, let's begin. Part of what makes space such a cliffhanger is how our perspective keeps changing. For most of human history, we thought the night sky was just a fancy ceiling. Then, telescopes came along and ruined that illusion completely. Suddenly, those twinkling dots turned out to be suns, and the dark patches between them were teeming with galaxies. It was as if we discovered the walls of our room were actually windows, and the view outside was infinite. The more we learn, the more confusing it gets. Space isn't just out there. It's expanding, stretching, moving. It's not a static backdrop. It's the stage, the props, and the script all at once. You can't step outside of it because space is the thing you exist inside of. Asking where it ends is a bit like a fish asking where the ocean ends while still underwater. The answer might be, "Buddy, you're not getting out to check." And yet, our curiosity doesn't quit. Humans have an unshakable need to find edges. We like borders, fences, finish lines. There's comfort in boundaries. They tell us where something stops and something else begins. But space refuses to cooperate. It doesn't give us edges, only horizons. It's as if the universe looked at our need for neat endings and said, "How about a sequel instead?" The funniest part is that even the concept of end doesn't make sense in cosmic terms. There's no cosmic wall, no glowing "the end" screen waiting out there. If space does have a limit, it's not something we can reach by traveling in a straight line. You'd just keep going, and the more you moved, the more space would unfold ahead of you. It's like trying to find the last page of a book that keeps printing new chapters as you read. Philosophically, The idea of an endless universe is both thrilling and terrifying. It means there's no final destination, no beyond space to escape into. We're trapped inside infinity, which sounds poetic until you realize that means there's literally nowhere else to go. But it also means the possibilities are endless, new worlds, new forms of life, new cosmic mysteries waiting to be stumbled upon by some curious species that dares to look up and ask, "What's next?" And maybe that's why the question of space's end fascinates us so much. It's not just about astronomy, it's about imagination. Space represents the unknown, and the unknown is where all great stories begin. Every time we point a telescope upward, we're really searching for our place in that story. We're asking, how big is this thing we're part of? And are we just background characters or main cast? The truth is, space might not have an ending, but it gives us a beginning every time we look at it. That's what keeps us hooked. The mystery itself becomes the reason to keep exploring. The night sky isn't a blank void. It's a never-ending question mark, glowing faintly in the dark, daring us to find out more. So where does space end? Maybe it doesn't. Maybe it's less of a finish line and more of an invitation. An endless conversation that the universe started and we're just learning to reply to. Space is the universe's version of a suspense novel that never closes, the ultimate cosmic cliffhanger that keeps us reading one star at a time. Imagine the loudest explosion you can think of. Now erase the sound, remove the smoke, delete the air, and stretch that moment across all of existence. Congratulations, you're still nowhere close to the Big Bang. It wasn't an explosion in space, it was an explosion of space. The universe didn't expand into something, it created the very something it expanded into. Before the Big Bang, there was no space, no time, no before for anything to happen. It's like trying to ask what's north of the North Pole. The question itself stops making sense. At the beginning, the universe was smaller than an atom, yet it contained everything that would one day become galaxies, stars, planets, and the occasional confused human wondering where space ends. This tiny singularity was unimaginably dense and unimaginably hot, so hot that physics as we know it breaks down trying to describe it. It's like the laws of nature looked at that moment and said, "Nope, I'm out." Then, in an instant, that little point of everything began to expand, creating not just matter, but the cosmic stage itself. For the first few fractions of a second, the universe was a chaotic soup of energy. Space was expanding faster than light, not because anything was breaking the speed limit, but because the limit didn't apply yet. The fabric of reality itself was stretching, dragging everything along for the ride. If you could somehow stand outside the universe, which you can't, you wouldn't see a fireball spreading into darkness. You'd see nothing. Because outside didn't exist yet. Space was making room for itself. This early expansion is sometimes described as cosmic inflation, but that term makes it sound calmer than it was. It was more like the universe's caffeine rush, a sudden burst that made everything larger in a blink of time. Imagine blowing up a balloon so fast that the air molecules didn't even have time to realize what was happening. That's inflation. Within a trillionth of a second, the universe went from microscopic to enormous, and it hasn't stopped stretching since. As it expanded, it cooled. particles began forming like protons and neutrons, which later teamed up to make atoms. Light finally broke free after a few 100,000 years, filling the universe with a warm, glowing afterimage known today as the cosmic microwave background. It's the oldest light we can see, the universe's baby photo, still faintly glowing all around us. If you've ever seen static on an old television, a tiny fraction of that fuzz is leftover radiation from the Big Bang. So, yes, the next time your screen says no signal, technically it's tuned to the dawn of time. The name Big Bang actually started as a joke. In the 1940s, a skeptical astronomer named Fred Hoyle used the term mockingly during a radio broadcast. Ironically, the name stuck, and now it's one of the most famous phrases in science. You could say the biggest event in history was named by accident, like calling the Mona Lisa that lady with the smirk. But behind the funny name lies the most profound truth we've ever discovered. The universe had a beginning, and it's still having consequences. Even now, billions of years later, galaxies continue to drift apart as space stretches between them. You're not sitting still right now. You're being carried by an expanding universe that's literally making more universe as we speak. If you could pause time and draw a giant grid over everything, you'd see that the lines between galaxies keep getting longer. The galaxies aren't flying through space like projectiles. They're being pulled apart by space itself. It's the universe's way of redecorating, endlessly rearranging the furniture without asking permission. But why did this all happen in the first place? That's the part science still doesn't fully understand. What caused the Big Bang? What existed before time began? Those are questions that stretch even our most advanced physics. Some scientists think the universe might have been born from quantum fluctuations, a random ripple in the void that sparked existence. Others suggest that our universe could have budded off from a larger, older one, like a cosmic offspring. And then there are those who think there was no before at all, that the Big Bang wasn't a beginning, but simply a transformation, the universe rebooting itself like a cosmic computer after a crash. Whatever the reason, the Big Bang didn't just create space, it gave us the rules by which everything in space behaves. Gravity, light, matter, energy, all of it emerged from that first moment. Every atom in your body, every planet, every star, all of it traces back to that tiny, furious beginning. When you look at the night sky, you're seeing the aftermath of the universe's first spark. It's not out there. It's the same energy and matter that once existed in a single searing point, now cooled and spread out into this vast, beautiful expanse. So, where does that leave us? We live in a universe that's still expanding, still stretching, still changing. It's like being inside a cosmic party that started billions of years ago and shows no signs of slowing down. The decorations keep moving, the dance floor keeps growing, and no one really knows who started the music or how long it will keep playing. The Big Bang wasn't just an event, it was an invitation. It didn't create a static universe to sit and admire, it set everything in motion. The stars we see tonight are the echoes of that first explosion of being. The atoms in your body are recycled stardust, the literal ashes of creation. You are, in every sense, part of the Big Bang's after-party. And, as the universe keeps expanding, so does our curiosity, forever chasing the edges of a cosmic celebration that may never end. If you could stand outside the universe and watch it unfold, you'd witness something that looks both majestic and absurd. Imagine a loaf of bread in an oven, dough swelling in every direction, raisins embedded inside. The raisins aren't moving on their own, but as the dough rises, they drift farther apart. That's our universe. Galaxies carried away from each other. Not because they're zooming through space, but because the space between them is stretching. The universe isn't a playground full of galaxies running around. It's a playground that's getting bigger while everyone's trying to stand still. This idea was first spotted by Edwin Hubble in the 1920s, when he looked through a telescope and noticed that distant galaxies all seemed to be moving away from us, and the farther they were, the faster they went. It wasn't that we were the center of everything, though humanity briefly considered that possibility with great enthusiasm. It was that space itself was expanding uniformly, carrying galaxies along like leaves caught in a widening river. That discovery transformed our understanding of the cosmos. Suddenly, the universe wasn't a fixed stage. It was a living, growing thing. Now, the expansion of the universe isn't like an explosion flinging debris outward. Explosions have a center, a starting point, a direction. The universe doesn't. Expansion happens everywhere all at once. There's no middle to measure from. It's not that space is stretching into something. It's simply that the distance between any 2 points increases over time. The universe is the ultimate open concept design. No walls, no edges, just infinite remodeling. Here's where things get weird. While galaxies drift apart, not everything is affected by expansion. Gravity has a say in the matter, too. Within galaxies, stars remain bound together. Planets keep orbiting their suns, atoms stay intact, and your coffee mug isn't getting any farther from your hand. Expansion only shows itself at cosmic scales, where gravity's grip loosens and space is free to do its endless yoga routine. Locally, everything feels stable. But step back a few billion light years, and the universe looks like a cosmic bubble bath. Galaxies as frothy clumps, drifting farther apart with every tick of time. As space expands, it stretches the light traveling through it. This stretching causes what astronomers call redshift. Light waves become longer, shifting toward the red end of the spectrum. It's as if the universe is quietly repainting everything as it grows older, tinting galaxies with a reddish hue as they drift away. The farther away a galaxy is, the more red-shifted it appears, because its light has been stretched for billions of years on its journey to us. So, in a sense, when we look at distant galaxies, we're seeing both their color and their patience. If you were to fast forward the cosmic movie, you'd see the galaxies moving farther apart at a pace that's actually accelerating. That means space isn't just expanding. It's doing it faster and faster over time. Scientists once expected gravity to slow the expansion down, like brakes on a car. But in the 1990s, observations of distant supernovae revealed the opposite. The universe's expansion is speeding up. Whatever's driving it isn't normal matter or even light. It's something invisible, untouchable, and completely dominating the cosmos. We call it dark energy, which is science's polite way of saying, we have no idea what's happening, but it's definitely weird. Think about that for a second. We live in a universe that's expanding faster than ever, and we don't even know what's making it do that. Every second, the fabric of reality is literally stretching, and we're all just along for the ride. On human scales, it's imperceptible, but on galactic scales, it's the difference between a universe full of neighbors and one where the lights are growing dim in every direction. As this expansion continues, the future grows lonelier. Billions of years from now, distant galaxies will move so far away that their light will never reach us again. The night sky will grow emptier, and the cosmic landmarks we use to understand our place in the universe will fade beyond detection. Future astronomers, if any are left, might look up and see only their own galaxy, surrounded by eternal darkness. They may never know there was once a vast cosmic web connecting everything. It's a bittersweet truth. The universe is growing apart, and there's nothing we can do to stop it. But that's not to say the universe is falling apart chaotically. The expansion is beautifully smooth. It's not tearing galaxies to pieces or shredding stars. It's just quietly, gently, making more space. You could almost say it's polite about it until you realize it's doing this everywhere, non-stop, forever. It's like the universe keeps adding rooms to a house that already has infinite square footage. The expansion also means the universe doesn't have an edge in the traditional sense. There's no boundary you can fly to where space runs out. Every point in the universe sees every other point moving away, just as we do. It's an equal opportunity expansion, with no privileged perspective. That's humbling, because it means no matter where you are, the cosmos looks roughly the same. Every galaxy is at the center of its own expanding view, a reminder that cosmic perspective is both relative and deeply democratic. And if you're wondering whether this expansion will ever stop, well, that depends on the tug-of-war between dark energy and gravity. If gravity somehow wins, the universe could slow down and collapse back in on itself, a scenario nicknamed the Big Crunch. If dark energy wins, and right now it's the undefeated champion, the expansion will continue forever, leading to what some call the Big Freeze, where everything drifts apart into cold isolation. There's even a third possibility, the Big Rip, where space expands so violently it eventually tears galaxies, stars, and atoms apart. You know, cheerful stuff. For now, though, we live in a universe that's stretching gracefully, a cosmic ballet that never quite repeats a step. Galaxies glide apart, light bends and fades, and the space between things quietly grows. It's easy to forget that this invisible motion is happening all the time, right under our noses, or, more accurately, between them. The universe is expanding, and so is our understanding of it. And in the end, maybe that's the most fitting metaphor of all. We're part of an expanding cosmos, one that refuses to stand still, constantly unfolding new mysteries faster than we can catch them. Imagine standing in a vast, dark field with a single flashlight. You can only see as far as the beam reaches. Beyond that, there's just darkness. The observable universe is kind of like that flashlight beam. But instead of batteries and bulbs, we've got photons and cosmic history. The limit of our sight isn't set by how powerful our telescopes are, but by how long light has had to travel since the universe began. That light speed limit defines the edge of what we can observe, the cosmic horizon. Beyond it lies everything we can't see yet, and possibly never will. Right now, that observable bubble around us stretches roughly 46 billion light-years in every direction. That's not a typo. It's 46 billion light-years, even though the universe is only about 13.8 billion years old. The math seems broken, but it's not. Space has been expanding the whole time light's been traveling toward us, so those galaxies have drifted much farther away than they were when their light began the journey. It's like getting a postcard from a friend who moved to another city, only to find out they kept moving while the mail was on the way. Everything inside this cosmic bubble is what we can see. The galaxies, the stars, the ancient light of the cosmic microwave background, all wrapped in a spherical field of visibility centered on us. But before we get too smug about that, here's the catch. Every observer in the universe has their own bubble. There's no special cosmic VIP section. If you were sitting in a galaxy 15 billion light-years away, your observable universe would also look like a sphere centered on you. That's the humbling part. Everywhere in the universe, someone's at the center of what they can see. It's cosmic egalitarianism at its finest. Now, inside our visible bubble, we've mapped billions of galaxies. Astronomers using deep sky surveys and infrared telescopes have charted a cosmic web. Filaments of galaxies woven together like an enormous three-dimensional spider's net. The bright nodes of this web are galaxy clusters, and the dark spaces between them are cosmic voids, vast expanses of almost nothing, the ultimate real estate for anyone who values privacy. It's stunning, but also deceiving, because this web represents only the visible portion of the universe. Beyond the reach of our instruments, the cosmic tapestry might continue endlessly, weaving patterns we'll never see. The limit of what we can observe isn't a wall or a border, it's more like the farthest horizon on an ocean. The light beyond that horizon hasn't had enough time to reach us, and since nothing can travel faster than light, it's forever out of range. Even if you waited another billion years, you would only see a little farther. The universe is expanding faster than light can cross it, so parts of it are moving away from us so quickly their light will never arrive. It's as if the universe is writing chapters faster than we can read them. The oldest light we can see is the afterglow of the Big Bang itself, the cosmic microwave background. When we detect it, we're not seeing stars or galaxies, but the first light that ever broke free, about 380,000 years after the universe began. It's the baby picture of existence, a faint, static hiss in every direction. That light has been stretched and cooled by billions of years of expansion, turning what was once blinding radiation into a soft microwave whisper that fills the cosmos evenly. Every time you heat something in your microwave, you're technically using the same kind of light that's been crossing the universe since the dawn of time. The scale of what we don't see is even more astonishing. Beyond our horizon, there could be regions of space completely unlike our own. Maybe the galaxies out there follow different patterns. Maybe the laws of physics twist slightly. Maybe there are structures so vast we can't even imagine them. But all of that remains hidden behind the cosmic curtain. The observable universe is less about the universe itself and more about our personal window into it. We don't know what's beyond the glass, only that the light hasn't checked in yet. This concept plays a sneaky trick on our minds. When we look out at space, we're also looking back in time. The farther we gaze, the older the light. The glow from nearby stars left them years ago, but the light from distant galaxies set off billions of years before Earth even existed. The farther we see, the younger the universe was. So, when we map the cosmos, we're really constructing a time-lapse photograph, different layers of history stacked on top of each other, all visible at once. Somewhere on that invisible timeline is the moment galaxies first formed, the birth of stars, the ignition of light itself. Our telescopes don't just peer into distance, they peer into memory. If you were to stand on the edge of what we can see, you would find no wall, no glowing border, no cosmic "here be dragons." You'd just find more space. Space that continues beyond our reach, receding faster than light, forever beyond our comprehension. It's a little like trying to read the last page of an infinite book. Every time you think you're close, more pages appear. The observable universe is simply the part of that story we've managed to glimpse so far. And here's the real mind-bender. Because light takes time to travel, we can't ever see the universe as it is right now. We can only see it as it was. Every starlit sky is a historical record, a fossil of photons that have been en route for eons. The universe we observe is really a memory of itself, unfolding before us in delayed broadcast. Somewhere beyond our horizon, new galaxies might already exist, their light still racing toward us, fated to arrive long after we're gone. So, when scientists say observable universe, what they really mean is everything we've managed to catch in the act of shining. Beyond that, we can only imagine. The rest of the cosmos is still out there, silent, hidden, unknowable for now. But that's the beauty of it. Our horizon isn't a limit of the universe. It's a limit of our time. As long as light keeps traveling, the story keeps growing. Somewhere beyond the darkness, the next chapter is already being written, waiting patiently for the light to arrive. Picture yourself on a small boat, floating in the middle of a vast, calm sea. The water stretches in every direction until it blends with the sky. You can see a perfect circle all around you, the horizon. But no matter how far you row, that horizon never gets closer. The universe works in a similar way. Our cosmic horizon isn't a wall, a fence, or a limit. It's simply the farthest distance from which light has had enough time to reach us since the beginning of everything. Beyond it, the universe doesn't stop existing. It just stops answering our calls. This horizon is like the ultimate line of sight, determined not by distance alone but by time itself. Light travels at a finite speed, about 300,000 kilometers per second, which sounds fast, until you realize the universe has been expanding for almost 14 billion years. That expansion means the space between us and faraway galaxies keeps stretching, even as their light moves toward us. So, when we talk about our cosmic horizon, we're really describing the farthest visible edge of spacetime, the region from which light, against all odds, has managed to cross an expanding universe to reach our eyes. Right now, that distance is about 46 billion light-years in every direction. Forming a giant sphere around us, inside that sphere sits everything we can possibly observe, every galaxy, every star, every wisp of ancient radiation still echoing from the Big Bang. Beyond that, the universe continues, but the light from those regions hasn't reached us yet, and some of it never will. It's like the parts of a movie that haven't loaded yet on a slow connection. You know the rest of the film exists, but you're stuck buffering. The cosmic horizon isn't stationary. It's constantly changing as the universe expands. New regions of space drift into visibility, while others slip out of it forever. You could think of it like a cosmic tide, with galaxies rising and falling along the boundary of what we can perceive. Except, instead of waves of water, it's waves of time and distance. The universe's expansion keeps redrawing the limits of our cosmic map, and we're always living right at the edge of what's visible. Here's where things get even trickier. The farther away we look, the further back in time we're seeing. The galaxies near the cosmic horizon aren't just far, they're ancient. We see them as they were billions of years ago, when the universe was young and the first stars were barely forming. If we could somehow travel there instantly, those galaxies wouldn't look like that anymore. In fact, most of them would have drifted much farther away or evolved entirely. So, the edge of what we can see isn't the edge of where things are, it's the edge of where things were. What lies beyond that cosmic horizon is one of the universe's most tantalizing secrets. Maybe it's more of the same. Endless galaxies, clusters, and cosmic filaments stretching on without end. Or maybe it's completely different. Regions of space warped by strange physics, where time runs faster or slower, or where the very laws of nature take a different shape. We simply don't know. The cosmic horizon is both a physical limit and an existential one. A veil separating what we can understand from what we can only imagine. Some scientists compare it to standing at the edge of a fog. Inside the fog, visibility fades gradually. You can sense there's something out there, but the details are gone. Similarly, we can detect subtle hints, tiny gravitational ripples, faint background radiation that suggests the universe extends far beyond what we can observe. Yet those clues remain fuzzy, as if the cosmos is teasing us with glimpses of a grander structure we're not equipped to see clearly. The concept of a cosmic horizon also raises a strange thought. Since light defines what we can observe, every civilization in the universe has its own unique horizon. Somewhere out there, an alien astronomer might be staring into their own sky, seeing a completely different set of galaxies. Their horizon overlaps with ours in some regions, but not in others. In a sense, every observer inhabits their own private bubble of reality, shaped by the light that's reached them. The universe is shared, but everyone's version of it is a little bit different, a cosmic mosaic of partial perspectives. It's humbling, isn't it? We're surrounded by a universe that's probably infinite, yet our vision of it is capped by physics itself. The cosmic horizon is like a built-in safety feature. No matter how advanced we become, we can never see everything. Even if we could travel at the speed of light, the expansion of space would still keep us fenced inside our observable bubble. The universe is expanding faster than light can cross it, which means some parts of space are permanently beyond reach. They're moving away faster than any signal, probe, or ambitious astronaut could ever chase. There's something poetic about that. The horizon isn't there to frustrate us. It's there to remind us how precious the visible universe really is. Everything we've ever known, every discovery, every glimpse of starlight, every cosmic revelation, comes from within that luminous shell. Beyond it, the universe remains dark and silent, like an unread chapter in a book we can never fully open. Yet even from within our limited view, the cosmic horizon gives us perspective. It's the line between the known and the unknown, a boundary drawn by the speed of light and the age of time. It marks the edge of our story so far, but it also whispers that there's more. Somewhere beyond that invisible curve, the universe continues, vast, mysterious, and entirely indifferent to whether we ever reach it. So, when you look up at the night sky, think of it not as a ceiling, but as a horizon. Every twinkling star, every faint galaxy is a ripple of light that made it across the vast sea of space-time to reach us. And just beyond that glow, unseen and unimaginable, the ocean of the cosmos rolls on endlessly, silent, infinite, and waiting for eyes that will never quite reach its shore. If you could step back far enough to see the entire universe, like really far, so far that even light would need a cosmic espresso to catch up, you might expect it to look like something simple, a big sphere maybe, or a sprawling web of stars. But cosmologists ask a far weirder question. What's the shape of space itself? Not just what's inside it, the galaxies, the stars, the dark matter, but the actual geometry of existence. What is the shape of everything? To understand that question, we have to imagine space not as a static backdrop, but as something that can bend, curve, and twist. Einstein taught us that space and time are like a stretchy fabric, what we call spacetime. Massive objects, like stars and black holes, warp that fabric, creating gravity. But what if the fabric itself, the universe on the largest possible scale, has a global shape too? Does it bend inward like a ball, outward like a saddle, or stretch flat forever in every direction? That's what scientists have spent decades trying to figure out, using math, telescopes, and a lot of patient head-scratching. Let's start with the simplest possibility, a flat universe. Flat here doesn't mean two-dimensional, like a cosmic pancake. It means that in 3 dimensions, space follows the familiar rules of geometry we learned in school. Parallel lines never meet. Triangles add up to 180 degrees, and if you go in a straight line forever, you'll never loop back around. In a flat universe, space extends infinitely in every direction, with no curvature bending it back on itself. If this is true, then our cosmos is infinite, not just vast, but literally without end. No edge, no wraparound, no boundaries. It's the kind of setup that makes both mathematicians and existential thinkers sweat. Now, let's bend that mental picture a little. Suppose the universe has positive curvature, like the surface of a sphere. In that case, space doesn't go on forever. It loops. If you travel in one direction long enough, you could theoretically return to where you started, like circling the globe. There's no edge, but there's also no infinity, just endless looping. In such a universe, the straightest possible path would eventually bring you home again. It's like living in a cosmic version of Pac-Man. Fly off the screen on one side, pop back in on the other. Then there's the negative curvature model, a universe shaped like a saddle or a Pringle chip, with space curving outward instead of inward. This kind of universe expands forever, but in a way that gives it an open, infinite geometry. If you could draw a triangle on this cosmic saddle, the angles would add up to less than 180 degrees. Space wouldn't loop back, but it would curve in a way that stretches endlessly, like an infinite roller coaster track that never flattens. So, which one do we live in? The answer, as of now, seems to be flat. Observations of the cosmic microwave background, the leftover glow from the Big Bang, have revealed that space is incredibly close to flat, with only the tiniest detectable curvature. That means parallel lines in the cosmos stay parallel, and light travels mostly straight across the cosmic landscape. But mostly is doing a lot of work here. Because even if the universe appears flat to us, it could still curve subtly over scales so enormous that we'll never notice. It's like standing on Earth and insisting it's flat because you can't see the curve from your backyard. Now, about that donut. The idea of a toroidal universe might sound like science fiction or breakfast, but it's a legitimate hypothesis. Imagine a three-dimensional version of a donut, where space wraps around in multiple directions. In such a universe, traveling far enough in one direction could bring you back from another, like playing interstellar hide-and-seek in a hall of mirrors. You could, in theory, see copies of distant galaxies or even duplicates of yourself, created by light looping around the cosmos and arriving back from another direction. Cosmic déjà vu with actual sprinkles. Scientists have searched for signs of such a wraparound effect by looking for repeating patterns in the cosmic microwave background, like a wallpaper design that tiles across the universe. So far, no clear repetitions have been found, but the idea isn't ruled out. It's possible the universe is much larger than our observable bubble, and any loops or connections are simply too distant for us to detect. If that's true, we might be living in a universe with cosmic hallways that connect back to themselves, an infinite maze disguised as open space. But the shape of the universe isn't just about geometry, it's about destiny. The way space curves affects how the universe evolves. In a positively curved universe, gravity could one day overcome expansion, pulling everything back together in a grand collapse, a big crunch. In a negatively curved or flat universe, expansion might continue forever, leading to a cold, stretched-out eternity. Geometry isn't just a shape, it's the universe's long-term plan. Interestingly, the shape of space also dictates how we experience time. In curved space, time can flow differently depending on where you are and how you move. On cosmic scales, that means the universe's geometry subtly shapes the passage of time itself. So, when scientists say the universe might be flat, they're not just describing its structure. They're describing how reality itself behaves, how light travels, and how time stretches between galaxies. It's mind-bending to think that we live inside a shape we can't step outside to see. It's like trying to describe the shape of a fishbowl from inside the water. We can measure, infer, and calculate, but we can never look at the whole thing from the outside. Yet, through clever observation and relentless curiosity, we've managed to sketch a rough outline. A universe that appears flat, but might curve ever so slightly. Perhaps looping back on itself in ways we can only imagine. So the next time you look up at the stars, remember, you're not just seeing lights in the dark. You're peering across the surface of a cosmic shape, tracing the gentle curve or perfect flatness of everything that exists. Maybe the universe is infinite, or maybe it's a loop, or maybe it's secretly a donut after all. Whatever its shape, it's big enough to hold all the questions we can possibly ask, and strange enough to keep us wondering what lies just beyond the curve. It's one of the strangest and most exhilarating ideas science has ever proposed. That our universe, the stars, the galaxies, the laws of physics, even the weird quirks that make coffee taste better than tea, might not be unique. What if we're just one bubble in an endless cosmic soda, surrounded by countless others, each with its own rules, realities, and recipes for existence? Welcome to the multiverse, the universe's way of saying, "Oh, you thought I'd stop at one?" At first, the idea sounds like pure science fiction, the kind of thing that lives between superhero movies and bedtime philosophy. But the multiverse isn't just fantasy. It's a serious scientific proposal that arises naturally from our best theories of cosmology and quantum mechanics. The notion of a single universe may simply be too small to fit what the equations are hinting at. One version of the multiverse idea comes from cosmic inflation, that dramatic moment right after the Big Bang when space expanded faster than light. Inflation didn't happen evenly. It may have stopped in some regions but continued in others, creating bubbles of universes that formed independently. Each bubble could have its own laws of physics, its own constants, maybe even different numbers of dimensions. Ours just happens to be the one where stars, atoms, and life as we know it are possible. If that's true, then reality is like a pot of boiling water, with new universes bubbling up endlessly from a cosmic stew of energy. This version is often called eternal inflation, and it paints a wild picture. Universes budding off universes, endlessly, forever. Some might last only moments, collapsing back into nothing. Others might grow vast and long-lived, filled with galaxies and life. The whole thing would be a cosmic foam, an infinite sea of expanding bubbles, each unaware of the others, floating in a higher dimensional reality. And somewhere in that endless fizz, ours is just one bubble among many, neither special nor central, just lucky enough to sustain observers who can ask why it exists at all. But there's another kind of multiverse. One born not from cosmic expansion, but from the mysterious depths of quantum physics. In the quantum world, particles don't have fixed properties until they're observed. They exist in a haze of probabilities. When you measure one, it chooses a result. But what if it doesn't actually choose? What if it splits? The many worlds interpretation of quantum mechanics suggests that every possible outcome happens, but in separate, parallel universes. When you flip a coin, in one universe it lands heads, in another tails, and in a third it lands on its edge just to be dramatic. Every decision, every quantum event, could spawn a new branch of reality. Somewhere out there might be infinite versions of you. One who took that risk, one who didn't, one who just ordered extra fries. These quantum worlds don't interact, but they coexist, layered like invisible pages of a cosmic book. Most of them would look very much like ours, differing only by small quantum details. Others might diverge wildly, entirely different histories, different outcomes, different physics. It's both comforting and unnerving to imagine that the universe might be recycling possibilities like a cosmic choose-your-own-adventure. A third kind of multiverse arises from string theory, which suggests that the universe's fundamental particles are actually tiny vibrating strings. For string theory to make sense mathematically, it needs extra dimensions, sometimes as many as 11. These extra dimensions could allow for a staggering number of possible vacua, or stable configurations of reality, each with its own physical laws. That number isn't small. It's estimated to be 1 followed by 500 zeros. That's 500 universes for every atom in your body, give or take a few. Somewhere out there might exist a universe where gravity is stronger, atoms are square, and water boils at room temperature. It's weird, but it fits the math. Now, if universes are out there bubbling and branching, could they ever collide? Some scientists think so. In the inflationary model, universes could occasionally bump into one another like soap bubbles in a sink. If that happened, the collision might leave a scar, an imprint in the background radiation of our universe, a faint bruise in spacetime itself. Astronomers have even searched the cosmic microwave background for circular patterns that might reveal where another universe brushed against ours. So far, nothing conclusive has turned up, but the possibility remains open. If one day we do find such a mark, it would be the first cosmic graffiti proving we're not alone. The multiverse also opens a curious philosophical can of worms. If there are infinite universes, then everything that can happen will happen, somewhere. That means there's another you who became an astronaut, another who's a medieval blacksmith, and probably one who's reading this sentence out loud to their pet octopus. Infinity guarantees not just variety, but repetition. Every possible combination of particles must exist somewhere, repeated endlessly across the cosmic landscape. It's like the universe's favorite trick. Infinite monkeys, infinite typewriters, infinite yous. Of course, not everyone in science is sold on the multiverse. Some argue it's untestable, a grand speculation that can never be proven or disproven because we can't see beyond our own universe's limits. If something can't be observed or measured, they argue, is it really science? Others counter that the multiverse is a natural outcome of theories that do make testable predictions. It's not an extra idea, just an unavoidable side effect of the math. In the end, the multiverse may be less about finding proof and more about stretching our understanding of reality. It reminds us that existence might be far stranger than we can perceive. Perhaps our universe isn't the whole story. It's just one page in a library with infinite shelves. And somewhere, out there in the cosmic soda fizz, another version of you might be staring up at their night sky, wondering the exact same thing. Are we the only universe out there, or just the one lucky enough to notice? Maybe the answer lies beyond our reach, or maybe it's bubbling closer every second, waiting to collide with us in a burst of cosmic déjà vu. Either way, one thing's certain, the universe we know may just be one of many, and reality itself might be far larger and far weirder than our imagination has yet dared to dream. If you thought the Big Bang was dramatic, what came immediately after makes it look like the opening act. The first fractions of a second following that initial spark, specifically from about a trillionth of a trillionth of a trillionth of a second onward, were pure cosmic chaos. But out of that chaos came something extraordinary. Inflation, a brief, furious episode when the universe didn't just expand. it ballooned. Imagine space as a stretchy fabric, and then imagine it suddenly deciding to inflate faster than physics should allow, doubling in size again and again in the blink of an eye. That's inflation, the universe's biggest growth spurt. Powered by laws of nature we're still trying to decode. To be clear, nothing within the universe was moving faster than light. Einstein's cosmic speed limit was still safe. Instead, the fabric of space itself expanded faster than light could travel through it. It's the cosmic equivalent of saying, "I didn't speed, the road just stretched really fast under my car." This expansion didn't fling matter outward into empty space. It created new space, pulling everything apart as it grew. The universe didn't explode into a void. It was the void, expanding itself at impossible speed. Inflation is one of those ideas that started as a mathematical patch and ended up explaining almost everything. Back in the late 1970s, physicists realized that the standard Big Bang model had some glaring problems. For instance, why is the universe so smooth and uniform, with galaxies evenly spread out instead of clumped into one side like a cosmic laundry pile? Why does space look the same temperature in every direction, even though light hasn't had enough time to travel across it and even things out? And why does the universe's geometry seem perfectly flat instead of curved or warped? These mysteries were cosmic headaches, until inflation stepped in like a cosmic handyman, tightening every loose screw. The theory goes like this. In the first tiny sliver of a second after the Big Bang, the universe was driven by an unstable field of energy, sometimes called the inflaton field. This field acted like a cosmic accelerator pedal, pushing space to expand exponentially. Every fraction of a second, the universe doubled in size, over and over, until it was trillions of times larger than before. Then, just as suddenly, inflation stopped. The energy driving it transformed into heat and particles, filling the universe with the raw ingredients for stars, galaxies, and YouTube videos about cosmology. This brief moment of hyperexpansion did something incredible. It ironed out the wrinkles of the early universe. Tiny irregularities got stretched so thin that everything became smooth and uniform on large scales. That's why, when we look at the cosmic microwave background, the ancient glow left from the Big Bang, it looks almost perfectly even in every direction. Inflation took a messy, chaotic birth and turned it into the calm, structured cosmos we see today. It's like the universe went through an intense yoga session before settling into its cosmic flow. But inflation didn't erase everything. It also magnified the tiniest quantum fluctuations, microscopic jitters in energy that existed before inflation began. Those fluctuations, stretched to astronomical sizes, became the seeds of galaxies and galaxy clusters. Every star, every planet, every cosmic wonder traces its origin back to those quantum hiccups. So, in a way, the grandest structures in the universe started as the smallest wobbles imaginable. The universe is, quite literally, built on quantum uncertainty, and inflation was the amplifier that made that possible. Here's where things get even more bizarre. Inflation might not have stopped everywhere at once. In some region, it could still be happening. That means our universe might just be one patch where inflation ended, while other patches kept expanding, forming new universes of their own. This idea, eternal inflation, suggests that the inflationary process is still bubbling away in some deeper cosmic fabric, endlessly creating new universes like a never-ending fireworks display. Each universe could have its own version of physics, its own constants, and its own fate. If that sounds familiar, it's because this is one of the leading scientific roots of the multiverse idea. Inflation might not just explain our universe, it might explain why there are so many. Now, detecting inflation isn't easy. It happened so early and so quickly that direct evidence is buried beneath billions of years of cosmic evolution. But scientists have found powerful indirect clues. The pattern of tiny temperature variations in the cosmic microwave background fits exactly what inflation predicts: a universe that's smooth overall, but with just the right sprinkle of irregularity. Those patterns are the fingerprints of inflation, frozen into the oldest light we can see. There's also the hunt for gravitational waves from inflation, ripples in spacetime left over from that explosive expansion. These waves would be faint but distinct, curling through the early universe like echoes of its first heartbeat. Detecting them would be the ultimate confirmation that inflation really happened. In 2014, one experiment briefly thought it had found those signals, but it turned out to be cosmic dust playing tricks. Still, the search continues, and every telescope aimed at the early universe is, in a sense, listening for the universe's first whisper. Inflation also carries a certain irony. It was meant to explain why the universe looks so simple, but in doing so, it revealed how strange it truly is. It tells us that the universe didn't just appear, it sprinted into existence, stretching faster than light, erasing its own chaotic beginnings. It suggests that our visible cosmos is just one bubble in a frothing sea of universes. And it reminds us that even the most familiar rule, nothing faster than light, has an asterisk when you're talking about the universe itself. So, yes, space cheated. It bent its own rules, expanded beyond imagination, and gave us everything we see today. Without that brief, frantic moment of inflation, there would be no galaxies, no stars, no us. The universe would still be a dense, uneven soup of chaos. Instead, it became a masterpiece of balance, vast, smooth, and full of wonder. Inflation was the universe's opening stretch, and it never really stopped reaching for more. Humans love boundaries. We like to know where things start and where they stop. Maps have edges, pages have margins, and even infinity signs have the decency to loop back on themselves. But the universe? It's the ultimate rule breaker. If you could hop into a spaceship, aim in any direction, and accelerate forever, you'd never crash into a cosmic wall or drift into nothingness. There's no edge to fall from, no invisible barrier waiting to say, "Congratulations, you've reached the end of existence." The universe isn't a box. It's a boundless shape with no outside. That idea can make your brain twitch a little. After all, if something exists, shouldn't it exist somewhere? What does it even mean for the universe to have no edge? To understand that, you have to think of space not as an empty container, but as a kind of flexible fabric, one that can stretch, curve, and even wrap around itself. In this fabric, moving in a straight line doesn't necessarily mean going off into infinity. It might mean looping back around, arriving right where you started, without ever changing direction. To picture this, imagine standing on the surface of Earth. You could start walking east and keep walking forever, circling the planet endlessly without ever finding a wall or an edge. The surface of Earth is finite. You can measure its size, but it's also unbounded, meaning there's no edge to fall off. Now imagine that same principle, but in 3 dimensions instead of 2. That's what the universe might be like, a finite yet unbounded space, curving around in higher dimensions so that straight ahead eventually becomes back home. This is what physicists call a closed universe. It's not closed in the sense of locked, but curved like a giant hypersphere. You can't see the curvature because space is so vast and smooth that, locally, it feels flat. Just like the Earth feels flat under your feet, even though it's round, space appears flat on small scales. Only by traveling immense distances, or observing the universe with cosmic precision, could you ever detect its overall curvature. And even then, it might be too subtle to notice. Now, if the universe curves back on itself, it raises a fascinating possibility. Maybe light itself can travel full circle. In theory, a beam of light sent in one direction could wrap around the universe and eventually return to its starting point. That means, with the right kind of telescope and a lot of patience, say, several billion years' worth, we could one day see the back of our own heads, cosmically speaking. You'd be observing light that left our galaxy long ago, traveled around the universe, and found its way home. It's like the ultimate cosmic selfie, except you're both the photographer and the subject. But what if the universe isn't curved at all? If space is truly flat and infinite, then there's no looping, no coming back around, just endless distance in every direction. You could travel forever and never return to where you started, because there's no curvature to guide you home. A flat, infinite universe has no edge either, but for a different reason. Infinity doesn't need one. It just keeps going. No walls, no boundaries, just more space, stretching endlessly. In that case, the edge of the universe becomes a meaningless phrase, like asking where the edge of a song is. However, not all cosmic shapes are simple spheres or endless planes. Some cosmologists propose more exotic topologies, spaces that twist and loop in strange ways. One popular example is the 3 torus model, which you can think of as a 3D version of a donut. In this model, if you travel far enough in one direction, you pop out the other side, just like in a video game map that wraps around. The universe could have multiple looping dimensions, connecting distant points in surprising ways. In a toroidal universe, the cosmos would be both finite and connected, a self-contained labyrinth of repeating paths. It's hard to grasp because our everyday intuition is built on things that have outsides and insides. The universe doesn't have an outside. There's no larger space it sits within. When people ask, "What's outside the universe?" the honest answer is, the question doesn't apply. Space and time themselves are what define inside and outside, and beyond them, those words lose meaning. It's like asking what's north of the North Pole. You've simply reached the limit of the map. That doesn't stop us from trying to measure the cosmic shape, though. Astronomers use subtle clues in the cosmic microwave background, the ancient light left over from the universe's infancy, to test whether space is curved or flat. If the universe curves positively, like a sphere, distant light would bend slightly inward. If negatively, like a saddle, it would bend outward. So far, all evidence points to the universe being astonishingly flat, within the limits of measurement. But flat could just mean it's so large that any curvature is too faint to detect, like trying to measure the curve of Earth using only your living room. Even the concept of an edge takes on new meaning in relativity. Space and time are woven together, so the shape of the universe isn't just spatial, it's also temporal. The edge of the universe, in one sense, is simply the limit of time itself, the moment of the Big Bang, beyond which there is no before. It's not an edge in space, but an edge in history. The universe doesn't end in distance, it ends in time. So, if you ever find yourself wondering where space ends, remember, it doesn't. The universe might curve, wrap, or stretch endlessly, but it refuses to give us a neat boundary. It's not a box we can peer out of. It's more like a cosmic illusion that folds endlessly on itself. You can't fall off the edge of the universe any more than a goldfish can swim off the edge of its bowl. The fish only sees water. We only see space. And somewhere, just beyond what we can observe, space keeps on bending, looping, and stretching. An endless road with no destination, where straight ahead might secretly be the long way home. If you've ever looked at our universe and thought, wow, this place seems a little too conveniently balanced, you're not alone. Physicists have been thinking the same thing for decades. The cosmos appears tuned with eerie precision. The forces of nature are just strong enough, the constants just right, and the conditions just stable enough to allow galaxies, stars, planets, and ultimately, life. It's as if someone played the cosmic version of Jenga and somehow didn't knock the whole tower down. But what if our universe isn't a one-of-a-kind miracle? What if there are countless other universes, each built with slightly different settings on the cosmic control panel, and we just happen to live in the one that didn't immediately collapse into chaos? This is the tantalizing idea of the multiverse's unknown neighbors. Other universes, each with their own unique physics, floating like bubbles in a vast, unseen ocean of reality. Some of those universes might look vaguely familiar, still filled with galaxies and stars, but others could be utterly alien. Imagine a universe where gravity is 10 times stronger, crushing everything into a pancake of despair, or one where it's too weak for stars to ever ignite, leaving behind endless darkness. Maybe there's a universe where atoms never formed because the balance between protons and electrons didn't quite work out, or where light moves slower than a sleepy snail, turning every sunrise into a week-long event. To grasp why scientists take this seriously, we need to talk about fine-tuning. The universe's fundamental constants. Numbers like the strength of gravity, the charge of the electron, or the rate of cosmic expansion are all remarkably specific. Change any of them even slightly, and everything falls apart. If gravity were a bit stronger, the universe would have collapsed before galaxies could form. If it were weaker, matter would have spread too thin to make stars. If the electromagnetic force were off by a fraction, atoms wouldn't hold together. We exist in a narrow sliver of possibility where everything lines up just right. It's like winning the cosmic lottery, except the odds are so absurd that many scientists suspect it wasn't luck. It was statistics. Here's the reasoning. If there are countless universes, each with different constants, then of course one of them would have the right mix for life. We just happen to be in that one because, well, we're here to notice it. It's a bit of circular logic, but it makes sense. Fish only wonder about water because they live in it. Similarly, we only marvel at our perfect universe because we happen to live in one that works. Somewhere out there, in universes where physics went rogue, there's nothing and no one to ask questions. So, what might these neighboring universes actually be like? Let's start small. Say, a universe where the speed of light is different. In ours, light defines the ultimate speed limit, shaping everything from time to causality. If light were slower, the universe would feel more sluggish, with gravity dominating and time itself moving differently. If light were faster, energy might scatter too easily, preventing matter from clumping into stars. Even a small tweak would make everything unrecognizable. Or imagine a universe with a different version of gravity. Not weaker or stronger, but repulsive. Instead of pulling things together, it would push everything apart. No galaxies, no planets, no cozy clusters of matter. Just an expanding storm of lonely particles, all socially distancing forever. On the flip side, a universe with supergravity would crush everything into oblivion seconds after birth, a short-lived cosmic disaster that barely qualifies as existing. And then there are universes where the quantum rules change. Maybe particles in those worlds don't come in neat pairs, or probabilities behave differently. You could end up with bizarre, stable forms of matter, stars made entirely of neutrons, planets that shimmer like crystal, or atoms so stable they never react at all. Chemistry, as we know it, might never happen. There'd be no biology, no life, no late-night existential pondering, just static perfection, beautiful but utterly inert. Some theories suggest universes could differ not just in laws of physics, but in dimensions. We live in 3 spatial dimensions and 1 of time. But maybe other universes have more, say, 10 dimensions, like string theory proposes. In those spaces, reality might be curled in ways we can't even visualize. Matter could move through directions invisible to us, and gravity might behave like a ghost, leaking between dimensions. To any hypothetical observer there, their world might seem normal, but to us, it would be a kaleidoscope of impossible geometry. If these universes exist, could they ever touch ours? Maybe. In the inflationary model, new universes constantly bubble into existence in the cosmic background. Occasionally, those bubbles might collide, creating a ripple, a faint scar in the cosmic microwave background, the radiation left over from the Big Bang. Astronomers have looked for these scars, circles or distortions that might reveal where another universe brushed against ours. Nothing definitive yet, but if we ever found one, it would be like finding fingerprints on the outside of the cosmic fishbowl. Proof that we are not the only bubble in the foam. Still, we may never truly communicate with our cosmic neighbors. Even if other universes exist, they might be forever sealed off by fundamental barriers, separated by more than distance, divided by different laws of space and time. They'd be close in a conceptual sense, but unreachable in every practical one, like reflections in a mirror that never meet. But that doesn't make the idea meaningless. The notion of unknown universes forces us to confront something profound. maybe our universe isn't special. Maybe existence itself is vast beyond comprehension, a multiverse of possibilities where every variation of reality gets its own stage. We just happen to live in the one that got the recipe right. Our universe might not be perfect. It wobbles, it expands, it ages, but it's stable enough to hold stars and curious minds that wonder about their place. And so maybe the cosmos really is a collection of infinite IKEA shelves, some sturdy, some collapsing, some assembled in ways that defy logic. Ours just happens to be the one still standing, a little wobbly, but holding together long enough for us to look around and say, not bad. And out there, beyond our cosmic walls, in realities we can't touch or imagine, there might be universes where everything went differently, where physics took another path, and creation wrote a different story. Unknown neighbors in an infinite neighborhood. Forever unseen, but perhaps just as real as our own fragile, miraculous bubble of existence. If there's one thing humans can't resist, it's drawing lines. We carve them into sand, sketch them on maps, build fences, walls, and even invisible borders in the sky. It's how we make sense of things, by splitting them into pieces. This side is yours. That side is mine. This is land. That is sea. This is earth. That's space. But out in the cosmos, those distinctions crumble like chalk in the rain. Space doesn't deal in tidy edges. It doesn't come with a finish line, "you are leaving the universe" sign, or a cosmic border patrol. Our obsession with beginnings and endings simply doesn't apply. When you stand on a beach, it's easy to believe there's a clear boundary between land and sea. But the moment you step into the surf, you realize that the line is an illusion. The sand and water are constantly trading places with every wave. The boundary isn't real. It's a temporary idea we impose on something fluid. The same is true for space. We want to believe it starts somewhere, ends somewhere else, and has a clear dividing line between here and out there. But space doesn't work like that. It's continuous, unbroken, and self-contained. Even the boundary between Earth's atmosphere and outer space is a human invention. We call it the Kármán line, about 100 kilometers above the surface, where the air thins and flight becomes impossible without orbital speed. It's neat, it's simple, and it looks great in textbooks. But it's not a hard edge. It's a gradient. Air doesn't suddenly stop. It just gets thinner, fading into the near-perfect vacuum beyond. If you could watch it without the drama of rocket launches and re-entry flames, you'd see there's no edge to cross, just a slow, invisible blending of one environment into another. That same illusion of boundaries haunts our understanding of the universe as a whole. When we ask, where does space end? We're really asking for a human-style border, some final frontier, a place to plant a flag or hang a "the end" sign. But space isn't built with edges. It expands, it curves, it stretches, but it never stops. The idea of an edge assumes there's something beyond it, an outside. But the universe has no outside. Space is not expanding into anything. It's simply creating more of itself. Asking what lies beyond space is like asking what's north of the North Pole. You've reached the point where the question loses meaning. This doesn't mean the question is silly. Far from it. It just means we're trapped inside our own frame of reference. We live in a world full of limits, so we instinctively project limits onto the universe. We think in terms of edges, because every experience we've ever had involves one. A table ends. A road ends. Even our lives have edges, birth and death, start and stop. So, when faced with something endless, our brains throw up their hands and start looking for a border that isn't there. The universe, however, isn't obligated to fit our mental templates. It exists in a way that defies simple geometry. For example, imagine standing on the surface of a balloon while it's being inflated. If you start walking in a straight line, you'll never find an edge, just more balloon. The surface itself stretches as you move, and if you keep going long enough, you could eventually loop back to where you started without ever encountering a wall. That's how cosmologists often describe space. Finite, but unbounded. It's a shape without sides, an existence without edges. Even the concept of a center is a kind of illusion. People sometimes imagine the Big Bang as an explosion from a single point, with everything rushing outward from a center. But that's not how it happened. The Big Bang didn't happen in space, it happened to space. Every point in the universe was once that center, and space has been expanding everywhere at once ever since. So, when you ask where the middle of the universe is, the correct answer is everywhere. Every galaxy, every star, every grain of cosmic dust shares that same origin point. You're sitting at the center of the universe, and so is everything else. And then there's the matter of time, because boundaries aren't just spatial, they're temporal. We imagine a before and after, a start and an end. But time, too, is woven into the fabric of space, and the Big Bang wasn't just the beginning of matter, it was the beginning of time itself. Asking what came before the universe is like asking what's earlier than the first second. It's a grammatical question in a reality that doesn't follow grammar. Time doesn't have an edge you can peek around. It simply flows from the moment it began. It's strange, though, how much comfort we take in edges. They give us closure, structure, safety. Yet, in the grandest sense, the absence of boundaries might be the most liberating truth of all. It means the universe isn't a box that confines us. It's a continuum that connects everything. There's no absolute separation between here and there, no rigid distinction between the cosmos and us. We are made of the same stuff as the stars, governed by the same physics, drifting through the same unbounded sea. Our need for boundaries is what gives rise to wonder. The horizon always looks like an ending, until you reach it and find more horizon beyond. Space is the same, an endless mirage of edges that vanish as you approach them. And maybe that's the real magic of the cosmos, not that it goes on forever, but that it keeps tricking us into thinking we're almost at the end, only to reveal that there is always more to see, more to learn, more to imagine. So, when someone asks, "Where does space end?" the simplest, most honest answer might be, it doesn't. Space doesn't end because it doesn't need to. The boundaries we crave are illusions, comforting lines we draw around the infinite to make it feel manageable. But the universe doesn't care for fences. It flows freely, endlessly, like a song that never stops playing, even when we can no longer hear the tune. When we look at the universe today, it feels alive. Galaxies twirl in elegant spirals. Stars are born in bright clouds of gas, and light from ancient worlds still races toward us, crossing unimaginable distances to reach our eyes. The cosmos is in motion, expanding, stretching, and evolving. But behind all that motion hides a quiet truth, one that's equal parts fascinating and tragic. The universe's story is a slow drift toward isolation. Space itself is speeding up, and in the far future, the stars we see will fade away, one by one, until the night sky turns dark forever. To understand where we're headed, we first have to rewind a little. After the Big Bang, the universe expanded rapidly, then gradually slowed down as gravity tried to pull everything back together. For a while, scientists thought that slowdown would continue forever, that the tug of gravity might eventually stop the expansion entirely, maybe even reverse it, collapsing the universe in a fiery finale known as the Big Crunch. But in the late 1990s, something astonishing was discovered. By studying the light from distant exploding stars called supernovae, astronomers realized the opposite was happening. The expansion of the universe wasn't slowing down, it was speeding up. That discovery was like finding out your car accelerates without a driver or a gas pedal. Something unseen was pushing galaxies apart, faster and faster, defying gravity's pull. Scientists gave this mysterious force a name that sounds simple but hides enormous mystery. Dark energy. No one knows exactly what dark energy is. It doesn't glow. It doesn't clump. It doesn't behave like anything we've ever measured. It's more of an effect than a substance, a property of space itself that drives expansion. The best way to imagine it is as a kind of anti-gravity, not pulling things together, but stretching the very fabric of reality. And it's not a small player. Dark energy makes up roughly 70% of the universe's total energy content. Matter, the stuff that forms stars, planets, and people, accounts for less than 5%. The rest, about 25%, is dark matter, another invisible substance that binds galaxies together. That means everything we can see, touch, or even detect is only a tiny sliver of what's out there. The universe is dominated not by light or matter, but by a silent force that's driving everything apart. As dark energy continues its work, galaxies far from us are accelerating away faster and faster. The farther something is, the faster it recedes, carried along by the stretching of space. That's not just poetic, it's measurable. Light from distant galaxies gets stretched too, its wavelengths lengthened by expansion, shifting it toward the red end of the spectrum. Astronomers call this redshift, and it's the fingerprint of an expanding universe. The redder the light, the faster the galaxy is fleeing. Some galaxies are already so far away that their light will never reach us, no matter how long we wait. They're moving faster than light, not through space, but with space. It's as if the cosmic fabric itself is pulling them beyond reach. Project that trend forward, and the picture gets lonely fast. In a few trillion years, most of the galaxies we can currently see will have vanished from view. Their light will never make it across the ever-expanding gulf. The Milky Way will merge with its closest neighbors, the Andromeda Galaxy and a few smaller companions, forming one massive galaxy adrift in isolation. Beyond that, everything else will end from sight. The universe won't shrink or end. It will simply grow too vast for its parts to see one another. We'll be cosmic castaways, floating on a raft of stars in an endless, dark sea. In this far future cosmos, astronomy as we know it will become impossible. Future observers, if there are any, won't see evidence of an expanding universe. The night sky will no longer glow with the light of distant galaxies and the cosmic microwave background. That faint afterglow of the Big Bang will have stretched so much it becomes undetectable. They'll see only their own galaxy, unaware that there was ever anything beyond. The universe will have erased its own history, leaving behind a deceptively small, quiet sky. This era of fading light is sometimes called the Cosmic Dark Age. But the darkness will deepen even further. Over unimaginable timescales, new stars will stop forming. The existing ones will burn out one by one, leaving behind cold remnants, white dwarfs, neutron stars, and black holes. Galaxies will dim, their lights winking out like the last candles in an empty hall. The expansion will continue regardless, dragging these extinguished worlds ever farther apart. Eventually, only black holes will remain, slowly evaporating over countless eons through a process called Hawking radiation. As they fade, they'll release the last whispers of energy into an ever colder, ever larger universe. When even the black holes are gone, space will be a vast, thin nothingness, an endless stretch of near-perfect emptiness, expanding into forever. The universe won't die in fire or chaos, but in silence. The last trace of motion will fade into stillness, the last bit of warmth into cold, and the last flicker of light into infinite night. And yet, there's something strangely beautiful about this ending. The same physics that will one day make the universe lonely is also what made it possible in the first place. Dark energy, mysterious and invisible, is part of the same fabric that gave birth to galaxies, stars, and us. Without expansion, there would have been no growth, no time for complexity, no space for life to emerge. The universe's acceleration isn't a failure. It's a continuation, a quiet unwinding of a story that began in brightness. When you look up at the night sky tonight, you're seeing the universe in its most vibrant chapter, a brief moment between its violent birth and its serene, distant future. Every star, every galaxy, every faint smear of light is part of a grand cosmic history still unfolding. One day, all of that will fade beyond reach, but right now, we're here to see it. The universe may be stretching itself thin, but we live in the moment when it still shines. It's a reminder that impermanence isn't the end of wonder. It's what makes the wonder matter. The universe is the greatest magician we've ever met. No matter how many tricks we uncover, it always has another one up its sleeve. Each time we think we've seen its furthest edge, it simply steps back, revealing another layer, another mystery, another reason to keep looking. It's as if the cosmos knows exactly how far we can see and waits just beyond that line, whispering, "You'll need a bigger telescope." From the moment Galileo first turned a crude lens toward the sky, every new tool we've built has shattered our sense of cosmic scale. His telescope revealed that the Milky Way's soft glow was actually millions of individual stars. Centuries later, Edwin Hubble peered through a vastly more powerful instrument and discovered that the Milky Way wasn't the universe. It was just one of billions of galaxies. Fast forward to today, and our telescopes can see light that's traveled for over 13 billion years, revealing galaxies forming when the universe was still a cosmic toddler. Every breakthrough expands the visible universe, and every discovery deepens the mystery. It's tempting to think that if we just keep building bigger telescopes, we'll eventually find the end. But that's not how this works. The edge of what we can see isn't a physical border. It's a boundary drawn by time, light, and our own ingenuity. The observable universe stretches about 46 billion light-years in every direction. But beyond that horizon lies a vast expanse we can't yet observe. Not because it isn't there, but because light from those regions hasn't had enough time to reach us. Even if we wait billions of years more, the accelerating expansion of space means some of that light never will. The universe's size is forever growing faster than our ability to comprehend it. In a sense, we're trapped inside a cosmic bubble, an ever-expanding sphere of knowledge that can never quite reach the outer limits of reality. We can only study the parts of the universe that have revealed themselves through light, radiation, or gravity. Everything beyond that is speculation. Beautiful, informed speculation, but speculation nonetheless. And yet, the unknown isn't empty. It's full of potential, full of questions, full of the silent promise that the universe still has surprises left to show. Our instruments have evolved from glass lenses to space observatories that float beyond Earth's atmosphere. The Hubble Space Telescope showed us a universe bursting with color and motion, a gallery of cosmic masterpieces painted in light. Then came the James Webb Space Telescope, a machine so powerful it can see the faint glow of the first galaxies ever formed. Webb peered into what we thought was cosmic darkness and found not emptiness, but structure. Galaxies forming sooner, faster, and more abundantly than theory predicted. The universe, as it turns out, didn't read our textbooks. Every discovery we make pushes the edge of understanding farther away. It's like trying to reach the end of a rainbow. The closer you get, the more it moves. Each answer generates more questions. What came before the first galaxies? What lies beyond the observable universe? What's the true shape of spacetime? Is there a deeper structure beneath it all? Some grand pattern that connects every particle, every force, every star? The further we reach, the less certain we become. There's a strange humility in that realization. Science often gives us answers, but in cosmology, it mostly gives us better questions. The deeper we look, the more we realize how little we know. And maybe that's the universe's greatest trick, not hiding its secrets behind walls, but scattering them in plain sight, daring us to look closer. Even the data we already have is a language we are still learning to read. Cosmic background radiation, gravitational waves, high-energy neutrinos, all of them are messages from the universe, written in codes we've only begun to decipher. Each carries a fragment of the cosmic story, a whisper from the earliest moments of time. When we detect them, we're not just observing space, we're listening to the echoes of creation. But like any ancient language, it's incomplete. There are gaps, distortions, and missing pages that might never be filled. And yet, that's what makes the pursuit so deeply human, The edge of understanding isn't a failure of science, it's its driving force. It's the frontier where logic meets imagination, where observation hands the baton to curiosity. Beyond the data lies the realm of theoretical physics, where equations become our AIs. Physicists use math like explorers use maps, charting terrains they can't yet visit. Some of those ideas, like string theory, quantum gravity, or higher dimensions, sound almost poetic, not because they're vague, but because they reach beyond what our senses can grasp. Maybe that's what the end of knowledge feels like, not a dead end, but a horizon that keeps retreating as we approach. Each step forward reveals more of the landscape and shows us how vast it really is. The universe isn't mocking us when it keeps secrets. It's inviting us to keep asking. After all, the moment we think we've figured everything out is the moment we stop growing. It's worth remembering that what we know now would have been unimaginable just a century ago. To someone from the early 1900s, the idea that space is expanding, that time can bend, or that black holes actually exist would have sounded absurd. But those absurdities turned out to be true, which means the mysteries we face today, the ones that sound impossible, like dark energy, quantum foam, or multiverses, might be tomorrow's obvious truths. The edge of understanding is always temporary. So, yes, space keeps laughing at us, revealing more of itself each time we look harder. But maybe that laughter isn't ridicule, it's encouragement. It's the sound of a universe that knows curiosity is its greatest creation. The end of space isn't something we'll ever find, because there is no end. Only the fading line between what we know and what we can still imagine. And as long as that line exists, as long as there's another mystery glowing faintly just beyond our reach, we'll keep looking up. Because the edge of understanding isn't where discovery stops, it's where wonder begins. There's a peculiar thing about curiosity. It never stays satisfied. Every time we peel back a layer of the universe, we find not answers, but more layers. It's like the cosmos is a grand onion of mystery, except instead of tears, it leaves us blinking in awe. And maybe that's the point. Maybe the purpose of exploring the universe isn't to find an end, but to realize there doesn't need to be one. When we look up at the night sky, we're really looking into time itself, seeing light that began its journey before humans even existed. Those faint pinpricks aren't just stars, they're stories. Each one tells of a moment in the universe's long history, a snapshot frozen in light. We point our telescopes at the heavens expecting data, and what we get instead are echoes of creation. And yet, even as we chart more galaxies and measure more cosmic details, there's always the same lingering feeling. We're still standing on the shore of an infinite ocean, watching the waves of light roll in, knowing there's a whole universe beyond the horizon. It's humbling, isn't it? To realize that the universe doesn't exist for our understanding. It doesn't pause to explain itself or slow down to let us catch up. It just is, vast, intricate, and breathtakingly indifferent. But within that indifference lies something beautiful. Because even though the cosmos doesn't owe us meaning, we can't help but look for it anyway. We turn chaos into pattern, randomness into rhythm, and the impossible into questions worth chasing. Our wonder is the bridge between what we can know and what we can only feel. For all our progress, we still haven't scratched the surface. We know what stars are made of, yet not what makes consciousness emerge from stardust. We can measure the age of the universe, yet not the reason it exists at all. We can trace the path of light across billions of years, yet still struggle to understand why it began shining in the first place. Space doesn't taunt us with its mysteries. It inspires us with them. It's a mirror that reflects our endless hunger to know more, to reach farther, to ask better questions. It's easy to think of exploration as a physical act. Rockets launching, rovers rolling, astronauts floating. But the truest exploration happens in the mind. Every discovery begins as a "what if" whispered into the dark. What if there are worlds beyond our own? What if we're not alone? What if the universe has no edge at all? Those questions are acts of rebellion against ignorance. Each one pushes the horizon of our understanding just a little farther away. Even the smallest moments of discovery carry that spark of wonder. When the first image of a black hole appeared, a dark circle ringed in fire, it wasn't just a scientific triumph. It was a collective gasp from humanity. For a brief moment, every person who looked at that picture was united in awe. That's what space does. It reminds us that beneath our borders and arguments, we all share the same sky. The universe doesn't stop at galaxies or cosmic microwave backgrounds. It extends inward too, into the atoms that make us, into the quantum worlds beneath our fingertips. The same laws that govern the orbits of planets also guide the spin of electrons inside your body. You are made of cosmic material, forged in the hearts of dying stars. Every breath you take is recycled starlight. That connection between the smallest particle and the largest galaxy is the universe's way of telling us that wonder isn't somewhere out there. It's everywhere, including within us. And the more we learn, the more wondrous it all becomes. Science doesn't shrink the magic of the universe. It amplifies it. Knowing that stars are nuclear furnaces doesn't make them less beautiful. It makes their beauty even more profound. Understanding that galaxies move apart doesn't make the night sky lonelier. It makes it more precious. Every fact we uncover adds another layer of awe, another reason to look up and whisper, "How?" Some people fear that one day we'll reach the end of discovery, that we'll map every galaxy, decode every law, and leave no mysteries unsolved. But that's impossible. The universe isn't a puzzle with a final piece. It's a living, breathing enigma that grows with us. Every answer generates new questions, and those questions generate wonder. Curiosity is infinite because the universe is infinite. We'll never stop exploring because there will never be nothing left to explore. Perhaps the most beautiful part of this endless journey is that it belongs to all of us. You don't need a telescope or a PhD to experience wonder. It's in the simple act of looking up, of realizing that those stars are both impossibly far and intimately familiar. It's in understanding that you're part of the same story as the galaxies, that your existence, tiny as it seems, still matters in this cosmic narrative. Maybe, in the end, the universe doesn't need to end because the story isn't about reaching its boundary. It's about learning to live with its boundlessness. It's about embracing the mystery, not solving it. Wonder is what makes the infinite feel human, It turns cold space into something warm, silent light into conversation, and emptiness into meaning. So maybe space really doesn't end because wonder doesn't either. The universe keeps unfolding, and so do we. We'll keep sending our eyes and our minds farther, chasing horizons that never stay still. And maybe that's the best ending possible. Not a finish line, but an endless invitation. Every dawn, every starlit night, every new discovery is the cosmos leaning close and whispering the same question it always has. What's beyond that?